Here's a graph of the exponential function 2 to the x. Just to remind ourselves a little bit about what we know about these sorts of exponential functions, let's state what the domain, range, and asymptote of this graph are. So the domain for the function 2 to the x is any x value that makes sense as an exponent. But as we discussed, any x value makes sense as an exponent on 2. So the domain for this function is all real numbers. For the range, remember the range of a function is all of the outputs that come out of a function. And looking at this graph, you can see that it seems like any positive real number could be an output for this function. All of the small positive real numbers are taken on as values off to the left, and all of the large positive numbers are taken as values for this function off to the right, and everything in between is kind of in the middle. This is in contrast to the negative outputs. So if you look at all of the negative y values, none of the graph never crosses any of the y values below y equals 0. And in fact, it never quite makes contact with y equals 0 either. So the range of this function is all y values greater than 0. Or I guess maybe a better way to write that would be to say that the range is the interval from 0 to infinity. All right. Also, this graph has a horizontal asymptote off to the left. The asymptote is y equals 0. It might look like there could be a vertical asymptote somewhere on the right-hand side of this graph, but because the domain of this is all real numbers and this function is continuous, in fact, there can't be an asymptote off to the right. So there is no vertical asymptote. It's just the horizontal asymptote to the left. All right, one final property of this function is that it's one-to-one. If you look at any horizontal line at any height, even below the x-axis, all of these horizontal lines cross the graph of this function at most once. The horizontal lines below the x-axis don't cross the graph of the function at all, but all of the other lines cross at most once. And that means that f is one-to-one. And as we saw earlier, any function that is one-to-one has an inverse. So the inverse function, f inverse, exists. So let's write down everything we can figure out about this inverse function. One thing we can do is sketch its graph. Remember, to sketch the graph of a function, you reflect the original graph across the line y equals x. And we can do that point by point as well. So there's the y-intercept of the function f is 0, 1, and that turns into 1, 0, and then this point up here on the original graph, 1, 2, turns into 2, 1, and 2, 4 turns into 4, 2, and then 8, 3, and then 16, 4, like this. And then going the other way, the point immediately to the left of the y-axis, this is minus 1, 1/2, turns into 1/2, minus 1, and all the other points sort of go down like this. And connecting this all up, we get a graph. Let's see if I can do it. Oops, not like that. We get a graph that looks something like this. Okay, I missed my points, but you get the idea. All right. And let's see if we can figure out the domain, range, and asymptote of the inverse function. Well, remember, inverse functions just switch inputs and outputs. The range is all of the possible inputs for the original function. Since the inverse function just switches inputs and outputs, that means the range of the original must be the domain of the inverse function. So the domain of this inverse function is from 0 to infinity. Looking at the graph, that makes sense. This graph is on the right-hand side of the coordinate plane, and that means that all of the x values on this graph are positive. it looks like the graph intersects the y-axis, but that was just me making a mistake drawing the graph. Okay, by a similar token, since the domain of the original function is all real numbers, that means the range of the inverse function must be all real numbers, because the inverse function just switches inputs and outputs. So it also switches domains and range. So the range of the inverse function is all real numbers. Finally, for an asymptote, well, you can see this graph flipping operation. It turned the horizontal asymptote at y equals 0 into a vertical asymptote at x equals 0. Okay, so there's some basic information about the inverse function for the 2 to the x function. Let's see if we can use this to evaluate this function, this new inverse function. So just as an example, let's look at, let's evaluate f inverse of, let's say, 64. All right, well, we don't know a lot about the inverse function yet. And when you don't know a lot about something, one thing you can do is give it a name and see if that helps. So let's call this y. So f inverse, actually let's call it c. So f inverse of 64, we're calling that c. But remember, an inverse function just switches inputs and outputs of the original function. So if we wanted to translate this into a statement about the original function, we could just switch inputs and outputs, like this. So f of c is equal to 64. But remember, f is the 2 to the something function, so f of c is 2 to the c. So we're looking for, c is an exponent now, and c is the exponent that we're putting on 2 in order to produce 64. Let's see, what exponent would that be? Let's see, 2 to the first is 2, 2 to the second is 4, 2 to the third is 8, and then 16, 32, 64. So 3, 4, 5, 6. It looks like 2 to the 6th is 64, so c is 6. But remember, c was just our name for f inverse of 64. Well, you can see what happened here is f inverse of 64 is the answer to the question. Sorry, let me phrase it as a question. F inverse of 64 is the answer to the question, what power on 2 produces 64? And it turns out that that's 6. Well, we could run through the same argument for any input for this inverse function. So if we run through the same argument but with a variable x as the input instead of the number 64, what we get is that this inverse function, f inverse of x, is the answer to the question, what power of 2 produces x. But you know, that's actually a familiar thing. You've probably run into this before. There's already a name for describing the power of 2 that produces x. And that name is log base 2 of x. Okay. So if this inverse function, f inverse, it's really log base 2. So if you haven't seen this notation before, this log base 2 notation, The 2 is, first of all, the 2 is not going into the function. It's part of the name of the function. Okay, so this function is named log base 2. And if you haven't seen it before, just think of it as the inverse function for the 2 to the something function. Okay. So this 2 to the something function, it has an inverse since it's 1 to 1, and we call that inverse function log base 2. All right, just to make sure we understand what log base 2 is doing, let's evaluate it for a couple other values, for a couple other inputs. So how about log base 2 of 1/2? So this is the answer to the question, what power of 2 would produce a half? So what exponent would you have to put on 2 to get a half? Well, that would be -1. How about log base 2 of the cubed root of 2? So again, think about 2 to what power would produce the cubed root of 2? Well, a cubed root is a 1/3 power, so the power would be a third. Okay, so really what this log base 2 is doing is it's extracting the exponent that you would need to put on 2. All right. So this whole mess started with looking at 2 to the x, but really we could have started with any base. So now let's consider b to the x. And b, since it's a base, b has to be bigger than 0. And also, for the resulting exponential function to be 1 to 1, b shouldn't be 1. Okay, so if we have an exponential function, b to the x, it is 1 to 1. 1 to 1. And so it has an inverse. Which we'd call f inverse. But the more usual name for this inverse function is log base b of x. Okay. And this is read log base b of x. And what a logarithm does is it answers the question. So f inverse of x is the answer to the question, what power on b produces x? So for example, let's evaluate log base 10 of 100. So what what exponent on 100 would produce 10? Well, to turn 10 to a power into 100, you'd square 10. You need a 2 up here, so that means this logarithm is 2. How about log base e of 1? So what exponent would you put on e to produce 1? Well, that would be 0. So log base e of 1 is 0. Okay. You can see logs and exponentials are two sides of the same coin. On the one hand, if you have b to the x equals y, you can rewrite this as a fact about logarithms. The corresponding fact about logarithms is that log base b of y is x. Okay. We can check that this is right because the right-hand side is saying the exponent we would put on b to produce y is x. But that's what the thing on the right is saying. It's saying if you start with b and you use x as an exponent, you get y. But that's exactly the same thing. All right. So every base, except for one, has its own logarithm. There are actually two special log functions. Base 10. Okay, log base 10 is often written as log with no base at all. Okay, so if there's no base down here, it's implicitly log base 10. This is called common log. This gets used a lot in the sciences. And the other logarithm that's sort of important enough to have its own name is, of course, base e. This should come as no surprise, because if exponential base e is somehow more important, then logarithm base e is also going to be more important. So log base e of x is given the name ln. I often will write it like this, so ln, and this is called natural log. Somehow base e is the most natural base for logarithms. If you have a scientific calculator, you'll probably notice that you have buttons for these two logs. On my calculator, they show up right here. Log base, the common log, that's log with no base, and which is really log base 10, and natural log, which is really log base e. Most scientific calculators don't have a logarithm button for any other base, which might seem like a problem, but really it's not. We'll see later on that there's actually a way to produce all of the other bases using just base e or just base 10. All right, so to sum up where we're at, every exponential function, except base 1, has an inverse function. That inverse function is called logarithm for that base. There are two special logs, log base 10, which is called common log, and log base e, which is called natural log.